Hello everyone, welcome back. Today I'm going to explain a problem on design for shear. A PSC beam 250 mm wide and 1500 mm deep is subjected to a shearing force of 900 kN. The fiber stress under working loads is 4 Newton per mm square. If the effective pre-stress is 1000 Newton per mm square and area of cable is 1500 mm square, design the shear reinforcement. The cable are inclined at an angle of the arc sine inverse 1 by 6. In the diagram, you can see this is a longitudinal section, this is a cross section. The cross section dimension is 250 mm wide. The complete depth or overall depth is 1500 mm and dt is measured from the center of the cable to the top. And in the longitudinal section, we have a parabolic cable. For that, tangent is drawn. It is having a slope. From the neutral axis up to the tangent is a slope. And here, shear won't be there in the horizontal direction. Shear on the beam will always be in the vertical direction. That is, beam shear is only in the vertical direction. So we should consider P sine theta has vertical component which is going downwards. Next is whatever data they have given in the question, we should write it down. That is, fiber stress FCP is equal to 4 Newton per mm square. Area of the cable is 1500 mm square. Pre-stress 1000 Newton per, effective pre-stress is 1000 Newton per mm square. Shear force is 900 kilo Newton. So let's start with the calculation. First thing is, we should find out external shear force. For external shear force, go back to the previous slide. In the question itself, they have given a shear force as 900. To get a ultimate shear force, we should multiply the shear force with factor of safety, that is 1.5. Therefore, VU will be 1350 kilonewton is nothing but ultimate shear force. Next is internal shear resistance, VCO. As this is a parabolic cable and along with that they have given a pre-stress and the angle, we should consider VCO is equal to 0.67 BD into whole root of FT square plus 0.8 FCP into FT plus P sine theta. If it was a straight cable, then we would have taken only this much. P sine theta would have been not there. Okay, it's a parabolic cable. Next is, first we should check do we have all the terms for substitution or not. We should cross check it. If we check that, we can clearly see this P is not there. Theta value they have given, P is not there. Even FT is not there. So let us start calculating with that. So let's assume grade of concrete is FCK equal to 40 Newton per mm square. Why did I take this FCK as 40 Newton per mm square means to calculate the tensile stress FT, we have a standard formula as 0.24 into root of FCK. So as in the question itself they have not given, we should assume this data of FCK. We will get 1.52 Newton per mm square has a FT value. Next is a calculation of P. We know the formula, pre-stress into area of cable will give us P. Pre-stress is 1000 Newton per mm square, area of the cable 1500 mm square. So if we multiply, we will get P value has 1.5 into 10 power 6 Newton. and sin theta is 1 by 6. Everything is ready, just substitute the value. So VCO is equal to 0.67 into 250 into 1500 into whole root of 1.52 square plus 0.8 into 4 into 1.52 plus 1.5 into 10 power 6 into 1 by 6 is a value. So therefore VCO is 922.36 into 10 power 3 Newton is a value. Next is we should compare VCO as well as VU. Okay, let's go back and check with VU value. Yes, here VU is 1350. What we have got from the calculation, we have got VCO is lesser than VU. So under that condition, we should provide shear reinforcement. For shear reinforcement, we are assuming 4-legged 8 mm vertical stirrups. It is just we are assuming. So now we should find out what is the area of the stirrups. Area of the stirrups is denoted by ASV is equal to 4, that is 4-legged, 4 into pi d square by 4. Here d is 8 mm. So it is pi into 8 square by 4. We will get 201.06 mm square. Next is we should find out a spacing for these vertical stirrups. That is by using a formula ASV by SV is equal to VU minus VCO whole divided by 0.87 into Fy into dt, where dt is found out by assuming the effective cover. We are just assuming 100 mm has a effective cover. So 1500 minus 100, we will get dt has 1400 mm. So other than SV, we know all other terms. 201.06 by SV is equal to 1350 into 10 power 3 minus 922.36 into 10 power 3 whole divided by 0.87 into 415 into 1400. So if we substitute, we will get SV has 237.65 mm. That is nothing but a spacing, and here I have just converted from kilonewton to Newton, so it is into 10 power 3. Next is minimum shear. For minimum shear, how much should be the minimum shears minimum spacing should be means we have a formula for that. ASV by B into SV is equal to 0.4 whole divided by 0.87 into Fy. ASV is 201.06 whole divided by 250 into SV is equal to 0.4 whole divided by 0.87 into 415. Therefore, we will get minimum spacing as 725.92 mm. Next is maximum spacing. How did we get these formulas is according to the code book of IS 1343, we have two standard formulas for maximum spacing. Like that, we have considered 0.75 dt has one formula and 4 BW has the second one. So let's find out how much is that. It will be 0.75 into 1400. We will get 1050 mm. Next is 4 BW, 4 into 250 is 1000 mm. In this, which one is the least value we should consider? That means in all the 4 values, which is the least value, which is the least value, we should consider that. So it is it is 237 is the first value. Here in terms of 700, 200, 700, 1050, 1000. In that, what we have done is we have considered the two least value. The first least value is 237. So I'm just rounding it off to 230 mm at the supports. You can read a statement here. Provide 4-legged 8 mm vertical stirrups at 230 mm center to center near supports and 725 mm center to center at midspan. This is a second least value we have got. So what we have done, see the diagram here, 230 mm center to center at the supports. Here as well as here we are providing 4-legged vertical stirrups, 8 mm vertical stirrups with a spacing of 230 mm. But at the center we are providing 4-legged 8 mm vertical stirrups at a distance of 725 mm center to center. This is how we can design for a shear. Hope you have understood. Thank you.